Good morning and welcome to the Delaware-Maryland 4R Alliance's virtual field day. Thank you for joining us this morning, and we are excited for you to hear some interesting and informative presentations on the 4Rs. The Delaware-Maryland 4R Alliance is a collaboration between agribusinesses, farmers, government agencies, conservation groups, and scientists. We're working with the hopes that one day every nutrient application in Delaware and Maryland is made consistent with the 4Rs, which is the right nutrient source, applied at the right rate, at the right time, in the right place. We are focused on increasing implementation of 4R practices to benefit the economic, environmental, and social well-being of our region and our farmers. To go over some of the logistics for this morning, you will notice that you are all muted and your video is off. We ask that you do not unmute your computers or turn on your video to avoid distractions during the presentation. If you have questions, please type them into the chat box, and after each individual presentation, there will be a question and answer period with the presenter. We are excited to be able to offer continuing education credits for today's program for Delaware, Maryland, and Pennsylvania nutrient management, as well as Certified Crop Advisor nutrient management credits. The link to fill out with your CEU information will be posted in the chat box and sent to participants at the closure of this program. Please ensure that you enter the correct information, including your certification number, for the CEUs you wish to apply for. Again, we'd like this to be an interactive process, so as you're listening to the presentations, please be sure to enter your questions in the chat box. We would like to take a moment to thank our sponsors for today's event. Without their support, today's virtual field day would not be possible. Sponsors for our event include the National Fish and Wildlife Foundation Chesapeake Bay Stewardship Fund, Corteva Agri-Science, ETS Environmental Tillage Systems, Mosaic, the 4R Nutrient Stewardship Council, and your host for today's meeting is the Delaware-Maryland 4R Alliance, a primary partnership between the Delaware-Maryland Agribusiness Association and the Nature Conservancy. Thank you again to our sponsors.
At this time, please welcome Mike Twining with Willard Agri-Service to talk about their program called EcoN.
Hello and welcome to the Mid-Atlantic 4R presentation on nitrogen modeling. My name is Mike Twining. I'm Director of Sales and Marketing for Willard Agri-Service. I'm a certified crop advisor, live in the state of Delaware and work in the Mid-Atlantic region helping growers manage nutrients in plant food, leading a team through Willard Agri-Service. I'm excited to be able to present today on nitrogen modeling. This is a relatively new and robust technology that farmers have an opportunity to utilize on their farms. It really lines up with our core value of being innovative. I'm proud to say Willard Agri-Service was the first to launch a fully functional commercial nitrogen modeling product in the Mid-Atlantic. There are many choices out there today for farmers to use, and I truly believe a rising tide raises all ships. This is a great decision support tool, and I'm going to talk today about that tool. So the outline of my talk is nitrogen modeling basics. We're going to show you some output from a nitrogen model, and we're going to talk about where nitrogen modeling helps a grower with compliance today and where we hope this technology lands in the future. So let's start with the basics. Nitrogen modeling basics. Nitrogen modeling is just a continued evolution of the adaptive management programs around nitrogen management on farms. Nitrogen's an interesting plant food in that it's a complex mineralization cycle. It is critically important to crop production, and it's something that we're getting better and better at managing as time and science goes on. We incorporate the nitrogen modeling tool into our eco-nutrition system, which is a decision support system to help growers with more advanced nutrient management. One of those nutrients is nitrogen, and I'm going to talk specifically about nitrogen today. So when you think about nitrogen management and nitrogen modeling, there's two very simple concepts that you need to understand. And one is when we fertilize our soils, we're doing just that. We're fertilizing the soil, and it is actually the soil that then meets the demand of the crop from a plant food standpoint. So as we apply nutrients to the soil, those nutrients, and the better job we can do with those nutrients of matching the demand of the crop, the less likely we are to have loss to the environment, and the more likely the grower is to have a profitable crop. So if you put it all together in terms of nitrogen modeling, what we're really doing is we're modeling those two key components of nutrient management. So we're modeling the crop growth, which then would help us understand better what the crop demand is. And we're modeling soil mineralization and nitrogen loss, which models the available soil nitrogen supply. So these are not new concepts. This is something that's gone on for as long as we've been doing commercial crop production. Nitrogen modeling is a tool, though, that gives us the ability to have greater in-season, real-time insights into these two critical components of crop production that, when you put them together, result in us understanding better how much nitrogen is required to achieve a realistic yield goal for every farm and field. A key point about nitrogen modeling, as with any kind of model, is it's a simulation of what's happening in the field, and the model is no better than the data you put into it. Now, what's unique about nitrogen modeling is as the season goes on, we do have the ability to correct the data real time if for some reason we discover that some of the data in the model is not accurate. So for instance, we model weather, and the model may indicate that any given field got a given amount of rain, that in reality, when you go out and check the rain gauge, you find out, no, it wasn't a half inch, it was an inch. Well, we can change that, and the model will adjust. We set the model at the beginning of the year to model rooting depth of the crop, which would be the available area the roots have to pull nutrients. And if we discover through scouting that maybe there's a compacted layer that's inhibited root growth, well, we can model a different root zone. Fairly dynamic tool that enables us to really better understand what's actually happening in the field and farms that we're working with. Why is nitrogen modeling a relatively new technology? Well, as you can imagine, trying to simulate the nitrogen mineralization cycle, all the different soil types that exist within any given operation, the weather, the growth of the crop, it takes a lot of computer horsepower to be able to do that. And it wasn't until around 2012 to 2013 that the computer technology caught up with the complex algorithms to enable us to run these models in real time. Since that time, the technology has really grown and has become better and better every year, and more accessible to a larger group of growers. So that's kind of the basics on nitrogen modeling, input and output with recommendation. To help you better understand that, let's look at an actual case study of a field right on the Delmarva, run through the nitrogen modeling tool within our eco-nutrition system. So we talked about the supply of the soil and the ability of the soil to supply nutrients to a growing crop. So where do we get that information? Well, one of the original adaptive management tools is a good old soil test. And when you look at a soil test, you get some very valuable information about the soils and the ability of the soil to supply nutrients. One is organic matter, one is cation exchange capacity. Those are two components that go into a nitrogen model. The next is a soil type report. And with this soil type map, we can determine whether we have a loam, a silt loam, a sandy loam, a clay. All those different types of soils have different capacities to supply nutrients to a soil. Some of the other very critical components to put into the model is what culturally, management-wise, has happened in that field. So what variety was planted and what's the maturity of that variety? Why is that important? Well, we track heat units in a nitrogen model, and we know that as the growth stages of corn progress, nutrient demand changes, generally increases and then drops off. The population would indicate overall nutrient demand. Planting date is certainly critical for purposes of tracking weather. We also input application dates and rates of all nitrogen sources, whether that's something like an animal manure or commercial fertilizer, as well as what's the cropping history of that field? What was the cover cropping history of that field? Are there other places that nitrogen could be provided to that crop that we need to account for? What you're seeing on the screen is a copy of a GIS-based planting map that was created at planting so that we know confidently what happened in this field at planting. Once you plug all that information in, you're now in a position to be able to receive a recommendation based on the current year's model. So what I'm going to do is show you this same farm from 2019 and 2020. There'll be a couple key concepts that I want to come back to. But one of the key concepts I'm going to show you is that there is more variability from year to year on a field or farm than there is variability within a field. So oftentimes when we think about GIS-based tools in agriculture, we think of precision ag. And that's a little bit of an oxymoron, in my opinion, in that, you know, precision is a relative term within agriculture. We're actually managing a dynamic biological system with a lot of variability that exists in it. And we've all seen the maps that show, and I'm going to show you a map that shows the variability within this field from a yield standpoint. But then I'm going to show you the difference between how this field behaved from a nitrogen management standpoint based on the weather and the planting conditions that occurred in 2019 versus what has occurred this year in 2020. And I think you're going to be pretty interested to see that. In this particular case, the field that I've stepped you through, this recommendation was generated on June 7th, 2019. And we put in 3 different yield goals just to see how the model would differentially recommend nitrogen based on those yield goals. The model does give you an absolute recommendation, but it provides a framework for you to use some judgment in that statistically there is a range within that yield goal. So if everything goes just right, you could probably achieve 180 bushels of corn according to the model with as little as 113 pounds of nitrogen. Or if some of the future end loss is a little bit greater than what it has experienced in the past, it may take as much as 141 pounds. It shows you how much fertilizer has already been applied. In this case, by June 7th of 2019, this field between starter and broadcast applications had received 62 pounds of commercial nitrogen. How much nitrogen had mineralized from the soil and the organic matter since planting is 6 pounds. How much had been lost since planting is 21 pounds. And that's an important factor to consider when you think about year-to-year variability. Gives you a virtual pre-side dress nitrogen test. And by the way, the pre-side dress nitrogen test is a proven long-time tool that we use in helping our customers make better nitrogen management decisions, particularly where their manure is. But the current technology that's approved is a snapshot. It's valid for that day, but it could change tomorrow if we get a different weather event. This tool updates constantly, and you can correct the model. So if we have a actual field PSNT, we can go enter that value into the model and say, no, here we actually went out and tested it. It wasn't 9, it was 12 on June 6th, and we can put in an actual PSNT and it will adjust the model. How much nitrogen the crop has already taken, and that's going to be based on the growth stage of the crop. That's why understanding the maturity of the crop is so critical. This particular output does not display the growth stage of the crop, but you can determine that it will display the growth stage of the crop and the complete recommendation. And then how much rainfall have we had since planting, which is 7.4 inches of rain, which is a fair amount of rain between May 3rd and June 7th. Previous crop in this case was soybeans, so there's going to be a credit for the carryover nitrogen from the soybeans. There's no irrigation. In this case, there was no manure applied, but it is important that you understand the model does incorporate all types of manures. And I decided to pick a relatively simplistic example because our goal here isn't to show you every possible permutation of the tool, is simply to demonstrate how it works. So what actually happened in this field when we did this? First, I want to take you back to the great thing about nitrogen modeling is it allows you to incorporate multiple technologies to manage adaptively the crop. We created this map based on the historic yield zones of the field, and we used this same zone to plant the crop. So these areas in green are the more productive areas of the field historically. And we built a planting prescription that there was more seeds per acre dropped in the green areas than in the historically less productive parts of the field in the red. We then turned around and said, we think the yield goals should be different for these zones. And if you remember, we had 3 different yield goals in the model. We were able to assign the green zone with one yield goal and the red zone another yield goal. On average, the nutrient management plan for this farm was written for 180 bushel field average yield goal. And in reality, the amount of nitrogen that was applied to this field matched up nicely with the model recommendation for 180 bushels. And that was 125 pounds per acre of side dress nitrogen. But we used some other technologies to adaptively manage the field and distribute that 180 pounds of nitrogen differentially. Now, if you'll remember, 2019, we had fairly wet conditions early, and somewhere around mid-July, the spigot cut off. This particular field experienced drought conditions, I would say from about the beginning of the second week of July through the rest of the life of this crop. And prior to that, had received adequate moisture, had a good stand. And at the time we were making these side dress recommendations, all indications were that we were well on track to having a crop capable of meeting our desired yield goal. Mother Nature has a way of not cooperating at times, and I would say it didn't cooperate in 2019. But the good news is, I think what we achieved was a really positive result, and a very environmentally positive result. These areas that you see in green are your higher yielding areas. And I probably can't do this real effectively, but if you rotate back and forth, what you'll see is that the areas that are historically more productive held true even in a dry year like 2019. That also corresponded to the areas that we applied more nitrogen. And while we didn't quite get to our stated yield goal of 180 bushels, we did a much better job of managing the nitrogen on this field to align with the yield potential, even in the face of bad weather. And our nutrient use efficiency remained very high as a result of using both of these adaptive management tools. So let's fast forward to 2020, and this farm is planted again in corn this year. Very, very similar soil types, and but a very different year. And I mentioned before, and I want to say it again, there is more variability year to year than there is variability within a field. And I really think the recommendations that the model produced in 2020 reflect this change in how dynamic the model can be in helping us make better in-season real-time decisions. So you may not have noticed, but in 2019, the 190 bushel yield goal called for 140 pounds of nitrogen to achieve that goal. And we had 62 pounds of nitrogen already applied. 2020, we had 48 pounds of nitrogen applied. And due to less loss in the field, the model only called for 105 pounds of nitrogen to achieve a 190 bushel yield goal. Pretty dramatic difference from year to year. While we've not harvested this field yet, I can tell you I have been out in the corn on this farm, and I have a high degree of confidence that we're going to achieve our desired yield goals this year. And we did it making a better decision based on the actual conditions of the 2020 growing season versus the 2019 growing season. With that, I'll transition over into the third leg of our presentation, which is present and future compliance. What is the goal of nutrient management? Well, it's to ensure the maximum utilization of applied and mineralized nutrients with a minimum loss to the environment. And currently, farmers have a good array of robust decision support tools to help them make better crop management decisions. In the example you just saw, we're using these tools to craft adaptive management plans that are comprehensive over the entire life cycle of the crop. These tools are critical to help our farmers comply with current and future nutrient management regulations, but most importantly, to also help them be profitable and sustainable long term. And really, our goal is to combine both of those things, and the goal of all the agronomists that I know is to combine those things to help growers be sustainable in their operation and grow their businesses while simultaneously complying with regulations. Unfortunately, the regulations that exist today do not specifically recognize nitrogen modeling as an adaptive management tool. The current recommendations, and I've cut this out of Maryland's manual, but my understanding is most states in the Chesapeake Bay watershed read in a similar fashion, that there is no direct reference to nitrogen modeling as an adaptive management tool. There is a reference in the footnotes that occurrence of a condition beyond the control of an operator, including unanticipated weather condition. Now, having my experience with this on an audit is that unfortunately nitrogen modeling falls into that category of discretion of the auditor during a plan, but we present it as documentation of what that anticipated weather caused from a crop production standpoint and how we responded. And it's a far more in-depth, detailed look at understanding what's going on in the field than the existing tools that we have, which includes just some judgment calls by experienced agronomists who perhaps have experienced similar years and what happened and try to make a prediction. Our goal is that as this technology continues to become more mainstream and used by a larger audience, that this tool will be recognized as an approved adaptive management tool in the regulation, similar to the other tools that currently exist, like soil sampling and soil testing, side dress applications, pre-side dress nitrogen testing. So that's a quick down and dirty look at nitrogen modeling. Hopefully you've picked up a thing or two about this as a result of this presentation, how it works, an example of how it works, show you some of the output, where it fits currently within the regulatory environment, and our hopes for the future adoption of this tool as an adaptive management tool. I want to thank the 4R Alliance for inviting me to speak on this important topic, and would welcome questions from anybody who's participated in the webinar or listens to it in a recorded fashion. Thank you.
Hello, everyone. If you have questions for Mike, you can throw them in the chat box. Right now, we don't have any for Mike, so I'll wait a minute for that. With that being said, I apologize for the inconvenience that some of you had today entering the meeting. For those who entered late, we will continue to put the CEU form that we ask for everyone to complete in the chat box. If you are on as a phone caller, we will email out the form with the registration. So if you registered, you will get the form to complete so that you get your CEUs. So thank you for your patience. All right, so we don't have any questions for you, Mike. Thank you so much for your time and for your presentation. We greatly appreciate it. Now we are going to move on to Todd Huskenker with Growmark FS, who's going to talk to us about soil sampling.
All right, good morning. My name is Todd Hunsaker. I'm my field specialist with Growmark FS. I cover quite a large area, so I cover the eastern part of Pennsylvania, basically Hershey East, all of New Jersey, and the Delmarva Peninsula for Growmark. Our My Field team is what we have branded our precision farming department. So I deal with a lot of grid sampling, data management, nitrogen solutions. So that's kind of my job. I help the sales force out with more technical things that they don't have time to take care of. So Lindsay and the folks at the 4Rs asked me to talk today about intensifying soil sampling and what's coming up next and what we're doing differently as far as soil sampling. So before we get into what's new, I think it's always important to go ahead and take a look back at what we traditionally have done for soil sampling in the past. So traditional soil sampling when I was coming out of college was pretty much this. I got handed a plastic bucket and a stainless steel probe, and a lot of my days coming out of college was spent walking or wandering, as I called it, around fields and pulling soil samples. So typically what you would do is you would take a zigzag path across the field, pull 15 to 20 cores, and end up with a bucket that looks like this at the end of the day for each field. You'd send those samples off to a lab, and you get a report back that looks a little like this, depending on what lab you use. You see you get your pH and phosphorus, potassium, magnesium, any of the elements that you wish to have, and your base saturations. So as we move forward, what we're looking to do is apply fertilizer or plant food to meet this critical level, where you don't want to over apply, because at that point you're wasting your capital on things that you don't need to, where you can invest that in other places. But you also don't want to undercut what you're doing and limit your yield. One of the other things that we really take a look at, and we'll look at more, is the effects of pH. So proper pH is critical for a lot of things, and you'll see this diagram here on the right. A lot of times you'll see this as that barrel end with the staves that are missing. And you'll see right here at the 6 to 6.5 areas where you can cover all of these nutrients and make sure that everything is available for your plants and able to just grow the best crop that you can. Low pH inhibits root development and growth, and high pHs can encourage nitrogen loss as well as low pHs. So it's important to have that pH ideal area. So my professor in college always used to joke, he said, if you stuck your feet in acid, you wouldn't want to grow real fast either. So that's why it's important to keep your pHs where you need them. So as we move forward and technology increases, we look at how in-field variation affects our crops. So a little example here, and for those of you with agronomic backgrounds and want to check my recommendations here, this slide was actually given to me by a coworker, so don't hold me too far to it. But if your soil test came back with a pH of 5.1, typical recommendations, depending on your area, would be about 5,000 pounds of ag lime per acre. If your pH came back at 6.8, you're in that ideal range already, so you're not going to be spreading any lime. If your phosphorus fertilizer recommendation came back at 9 pounds per acre, you would apply 220 pounds of P2O2 or P2O5 per acre. Depending on what phosphorus source you're using, that number of fertilizer would change. Same as if your analysis came back with a value of 105 pounds per acre, you wouldn't need to apply any phosphorus to that field. We know how important that is down on the Delmarva with the Chesapeake Bay just right in our backyard. That phosphorus is always being scrutinized if we need it or if we don't need it. So something to keep an eye on there. And then the same thing comes into play here at the bottom of this page for potash recommendations. And you can see there's two different potash recommendations, not real far apart compared to some of these other ones, but at the same point, if you're spreading this over hundreds or thousands of acres, that does add up in the end. So something to consider is, what if all of those recommendations came from the same field? In this case, we were looking at about a 30-acre field, 29.5-acre field. The pH in that field varied from 5.1 to 6.8. So it's really simple if you had those recommendations in front of you and they were different fields, and you're able to say, well, I need to spread lime on this field, but I don't need to spread lime on this field. But if you're looking at those recommendations and all of a sudden those recommendations are for the exact same field, you'd be applying approximately 2,500 pounds probably across the whole field. And you wouldn't be fulfilling either of your goals. You'd be over applying lime in an area that's already a 6.8 and in that ideal area, and you'd be under applying in some of those areas where you needed 5,000 pounds of lime. So look at it visually. This is that same field we were talking about, and you'll see on this map that we do have that variation all the way from 6.7 here, all the way down to 5, 5.0. Probably we would round down in that situation. So this is typical in a lot of fields that we look at, that maybe they don't. This is the corner of the field where back in the day, this is where the lime pile was dumped. And then if there was a little extra, we always would just spread it right on this piece so we could get done and get to the next field. In the same aspect, our phosphorus and potassium levels often have that same type of thing, especially phosphorus if this is where we dump the manure pile and then made an application. With crop nutrients, it's also indicative that if you have higher yielding areas of the field, we will actually see lower nutrient values because those plants are able to use more of the nutrients when they're growing rapidly and they're using more. So as we move into intensifying our soil sampling, here's some different things to consider. When you are deciding you want to intensify your soil sampling, how do you want to divide your fields? Do you want to use a grid or do you want to use zones? And some of my colleagues now that go out to me to the InfoAg conference every year, we joke around that there's always a long discussion about grids versus zones out there. And at the end of it, we never know what the right answer is, and we always joke around about that. Some other things to consider is your equipment needs. Variable rate application equipment is what I'm talking about. So if you're used to applying your own fertilizer or your own lime or even your own manure, is the equipment that you have able to be retrofitted to do variable rate application? Will you need to hire a custom applicator to do some of your application for you this year? Does the custom applicator that you normally have variable rate ready equipment? GrowMark FS has equipment in the area down in the Delmarva, so if that's something that you're looking into doing, certainly give them a call. We can certainly do any of that type of application. For people that are doing their own sampling, are you going to want to undertake the extra sampling that's needed for grid or zone sampling, or are you going to have your trusted advisor do some of that sampling for you, so you can free up your time to do other things that are probably more important in your operation, and let someone who deals with it on a regular basis take care of your sampling. The first thing we're going to look at is that grids versus zones question. So we'll start off looking at grid sampling, and then we'll move into zones from there. So when we talk about grid sampling, the big thing we look at is this is a man-made grid. So in the Midwest, grid sampling is just squares because they take a big square and divide it up into little squares. In our topography, a lot of times we'll end up with some odd-shaped grids, and that can follow some contour lines, or if there's hills in the area, we will sometimes put that line along a hill. But for the most part, this is a man-made grid that we would draw prior to heading out to a field to do soil sampling. So typically a grid sampling is going to be a faster process because as a soil sampler, I'm able to draw these grids prior to going out to the field. And then when I get out to the field, I can pull up these grids on whatever device I'm using to pull sampling points. So in our case, we utilize an iPad system along with a GPS system in the cab of our trucks for doing soil sampling that can guide us to these points. In a lot of cases, your grid sample will have a point here in the middle. We call that point grid sampling. So typically a sample company or person would drive their truck, four-wheeler, whatever piece of soil sampling equipment they have out to this point. And from here, they have a set distance diagram that they will draw sample from. So they will pull their 15 to 20 cores in probably a bullseye shape around this point. We'll talk about a bit later about using grids to create zones as well, and how that can differ from grid point sampling. So here's that similar field, and when we look at these 2 points, you'll notice that at the top here, this is potassium levels and pH levels. So in this field, we had a very high potassium level up top here and levels decreasing down here along the bottom. In our system, we have this set up as a low, medium, high. So your red areas of the field are those low areas that we saw on that soil report, and the top of the field here in green areas are going to be your good areas. Just visually appealing for us and our customers, kind of give you an idea. If you have your soil samples back and you see a lot of red and orange, not to panic, but know that there is some work to be done. And if you get a nice report back with green all over it, then maybe your salesman that's looking to get some fertilizer sold is going to be upset, but at the same time, we're looking to make good decisions on your farm, so we can certainly handle not needing to sell too much fertilizer. On your pH maps, and this one's definitely hurting, and this particular situation, this 4.6 down at the bottom, we were talking with the grower. This is actually a tomato field, and this bottom portion of the field here is where actually they would load the trucks with tomatoes after they were done picking. So I have a feeling that there was quite a bit of tomatoes dumped here at one point, and that was affecting their soil pH. The rest of the field, I don't know if they have much of an excuse for, but certainly after we did these samples, they were happy that we did them so they could get some lawn put on this field. Now these two, this example here was of a 2.5 acre grid. We do grid sampling anywhere from 10 acre grids on very large fields, all the way down to I've done 1/4 acre grids. That gets a little less cost prohibitive, but definitely gives you a whole lot more data. This next example we have here is of a 1 acre grid, and you'll see obviously these grid sizes are going to shrink, and that gives you more data points per field. So if you're looking to get more precise with your fertility, or if you know that you have an issue in certain parts of a field and we want to dial in and see what some of those issues are, it's much easier to go in there with a 1 acre grid because we're pulling a whole lot more data points per field. So you'll go in and you'll have a lot more information to see what was going on. And you can look right here with this 44 in the middle of the field with their phosphorus that they had done 2.5 acre grids. This would have got averaged in here, and they would have never seen that there was a problem here at this part of the field. pH-wise, on that same field, not a whole lot to complain about there if they're the grower. High pHs, so we're not even looking to make any type of applications here. So that's kind of what grid sampling is. And now we're going to move into zone sampling and the different ways that we can create zones. So I like to think of zone sampling as taking existing data so that we can soil sample areas of a field that are more similar. So there are a couple different ways that we go about this. The easiest way is to take those SSURGO maps that were made back in the 70s and take those and make zones out of them. So it's very easy for us to pull up those SSURGO maps. You have a different soil type, you pull a zone sample in that area, and it's easy to do because much like grid sampling, we can make those zones before we ever have to go out into the field. Various soil mapping is, or EC mapping as we can call it, is another way, and we'll talk about how the Veris Soil Mapper works, but this is a way to use technology to create probably a more accurate soil map than what we had from the SSURGO maps from the 70s. And these last two are very similar in the fact that a lot of times your satellite or field health imagery correlates very well with your historical yield data. So you have a plethora of yield data laying around, we can take that yield data and make zones out of it based on high yielding areas versus low yielding areas, and then go back and pull soil samples from those areas. And a lot of times your historical yield data and your field health imagery can correlate back to that Veris soil mapping data. So the first thing we're going to look at is just a SSURGO map, and I know a lot of folks have already seen these, but we're going to just go through and kind of show you that what a SSURGO map looks like, and then we'll move on to some of the other stuff. But this is a field here at my home farm, and we actually ended up Veris soil mapping this as well. And we did divide out this field in similar areas, but there was definitely more definition in that Veris soil map. So something to consider. This is a great place to start. And if you want to get more detailed in the future, we can always run that Veris over the field and figure out what we need to do to make it better. So when we're making EC zones or Veris zones, this is the setup we have. So we pull our Veris machine around with a pickup truck at the current moment. They're looking into maybe getting us a side-by-side to use, but this is the most convenient, and as long as soil conditions are okay, we don't cause a whole lot of compaction. We reduce the air pressure in the tires and can get around a little easier because we don't have to worry about trailering the sampler around. This pulls down the road very well. So the concept of the EC machine, as you can see, these discs here will go into the ground, and they emit a small electrical current into the soil. And based on how fast this current comes back to the other discs, it gives an EC value. Now, it's important to know that this value could be different on different days. So if you're wanting to get a whole field done, don't have them do half of it and then come back another day because your data will be inconsistent. So as we're driving across the field, this is the controller in the cab, and you'll see red areas are lower EC areas and green areas are higher EC areas. So these red areas, the electricity took a longer time to come back. So these are going to be lower yielding areas of your field, or like a lower soil type. Your green areas would hold more moisture, so your electronic conductivity would come back faster, and therefore you're able to predict that these are going to be your high yielding areas of the field. So we can make recommendations based on that. In this case, we take a look at this green area in the field here, and we can see on this picture a difference in plant health just in the corn stubble that was in the field as we were taking this Veris data. This is just an example of how this data is processed. So simply put, this all gets loaded into our system, and we can create zones out of it, longitude, latitude, and the values. And here's that same field that we were in. And you can see we divided this out into some zones, and you'll see the zones in the next slides here coming up. So in these images here, these darker brown areas are going to be your high EC areas, medium, and then low EC areas. And then we went out and soil sampled these. So you'll see these C, B1, and A, and B2 at the time we were using letters to do our sampling. And then we get the results back. So you can kind of see here about how these nutrients are interacting in the field in these zones, and about how your pHs are different in these zones. So we're able to make recommendations based on these zones moving forward. And here's an example of a recommendation that we would load into a spreader truck. Here's an example again about how if we compared our EC zones to those SSURGO soil type maps and what they look like. So definitely an updated, more specific map to what they had in the past. So as I said before, another way to create some of these zones is to use imagery or yield data. So this is an example of an image. I think on the left here, we have actually some yield data. So you can see how those images correlate. And then we're able to make zones from those images and then go out and soil sample. So this is an example where we used those zones, and these are the results we got back. So you go back and look, higher yielding parts of the field, lower potassium values in the field. So these plants were using this, using up the fertility in the middle of the field. And in a lot of cases, in certain places, we have deer feeding along the outside where yields were limited from outside factors. So the last thing we talked about earlier is how you're going to apply this. So when we talk about this in-field variation and you go, well, Todd, we took these soil samples and now we got to spread this. How am I supposed to know where to spread what? That's where it's important to have a piece of application equipment that's able to do variable rate applications. So 2 examples here of variable rate prescription. So this is a lime prescription and this is a fertilizer prescription. We load these into any of our variable rate able trucks, and then we are able to continue to keep spreading. So as we drive across the field, the chain or belt in the spreader increases and decreases and allows us to vary that rate of fertilizer without having to stop and make adjustments. You can see here, and we actually got a complaint call about this because the customer didn't realize that there was a certain part of the field that was getting a 0 rate. So he called up and said, hey, you guys didn't spread the whole field. What are you doing? But you can see in the prescription here, the line that was here along the edge where there was a no rate because these pHs were already good. So when we talk about completing your grid sampling, we have invested at GrowMark into some high-tech soil samplers. We have 2 Falcons now, and this is an automated soil sampler. I'm going to go through pretty quick here how it works and just give you an idea. If anyone has any questions about how it works, certainly my contact info is at the end of the presentation. We can certainly talk about that. But as we started doing more of this grid sampling and intensifying our soil sampling, realized that we were either going to need to hire a whole lot more people to walk around fields and pull soil samples or invest in some equipment that can do a better job. So you'll see here we have our Falcon soil sampler hooked up to our pickup truck, and I'll give you kind of a rundown of how it works. So we have this stainless steel drum that is ground driven when we're pulling a soil sample. So we'll lower this drum, and you see the probe at the top here. This is the close up of the probe. The probe is what is taking the sample. So the probe goes into the ground, your soil sample is pushed into this drum. All along while we're going through the field, your sample is being continuously mixed. So we're getting a very homogeneous mixture of your soil. So we're able to collect more samples and mix them together to get a better sample. When you're finished, we have a controller in the cab of the truck. We're able to hit finish sample. This funnel swings into the drum, and we're able to fill our soil sample bag on the back. When we're finished with that sample, we actually get a new bag that's pulled right under that funnel again. We're able to do 12 samples before we ever have to get out of the truck. So when we compare sampling by hand or with an ATV sampler, we're getting 15 to 20 cores per sample, and you can sample in a variety of conditions. Our Falcon soil sample, we're pulling 40 to 60 samples, 40 to 60 cores per sample. So in each acre grid or 2.5 acre grid, we're pulling 40 to 60 samples. Randomly chosen sites is something that's very important with the Falcon. Every 15 feet, no matter what I am doing in the cab, there is a sample being pulled. So that eliminates that human element of soil sampling. As you're driving through the field, it's continuously mixed. So that's also beneficial. And the soil that fills this drum will easily fill, a bucket and a half, a 5-gallon bucket and a half. So we're getting 7 gallons of soil that's in this drum. We take our sample out and then deposit the rest of the soil back into the field. So what's the goal here with intensifying our soil sampling? We want to provide a comprehensive cropping plan that balances field pH for optimized nutrient use. We're also maximizing our return on investment for our cropping inputs while minimizing the environmental impacts that farmers have. We want to practice practices that are beneficial to both agronomic and environmental. This kind of sums it all up here with the 4 R's nutrient stewardship. So everything I said back before was we want to make good choices for our farming operations to maximize your profits, but at the same time, we don't want to sacrifice environmental issues as well as what people are talking about. And I think more and more we see the social aspect with social media and how people view farmers and what we're doing. So it's important to do that. So yeah, we're gonna talk. We talked about using the right source in the right places today, and timing as well. So we covered a lot of the 4 R's today in our talk, but I will leave some time for questions. My contact information's here. If you have any questions about any of the things we talked about or anything else precision farming related, feel free to give me a call, shoot me an email. I'm happy to come down in the area and visit with you all if you need. So thank you.
Hello, everyone. Thank you, Todd. That was a wonderful presentation. Also, I would like to point out that we had a lot of great questions for Mike in the chat box, and Mike was able to answer them. So if you wanted to scroll through them, you guys are welcome to check them out. We're right now waiting to see if anybody has questions for Todd to answer live, but if he does not receive any, then he will respond via chat. All right, Todd, we have one from Sally. She said, how many acres are you doing these practices on?
Okay, so as a company, I think we are up around 20,000 acres that are currently in our grid/zone sampling, dependent on the region that we're in. So that's our whole Mid-Atlantic, PA, New Jersey, New York, and the Delmarva.
Thanks, Todd, and thanks, Sally, for that question. So, all right, we had 2 more questions come in. It says, what is the width that you use between passes with the Falcon?
So the Falcon really depends on the size of the field and the size of the grid. So if we're doing 1 acre grids, we're going to need to have much more narrow passes to get our 50 to 60 samples in that one grid. The bigger the grid, clearly the wider we can make those passes without having too much soil in the drum. So it really depends on the situation. But I would say it's 40 to 50 feet in 5 acre grids, and then anything under 1 acre grid, it's very tight passes to get our sampler through those smaller grids.
Thank you. And we had another question that says, what time of year is best for EC mapping?
Our rule of thumb really is if we have good soil conditions. So as long as the ground's not frozen and it's not too hard. So if you have a lot of clay, sometimes it's hard to get the discs in, but really planting conditions is the rule of thumb for us to pull the Falcon. Is just if you can run a corn planter through the field, we'll certainly be able to get good data and not cause any compaction issues while we're doing our EC mapping.
Thanks, Todd. And we had another one that says, how often are you doing grid sampling per farm? And every time there is a new set of soil analysis.
So grid sampling depends on what type of soil sampling program they're on. If they're used to sampling every year, I have customers that we're pulling new grid samples every year, and then you get a new set of soil, a new soil analysis back. There's also customers that are utilizing yield data in those off years, so they're not pulling soil samples every year, but they're pulling soil samples every other year, or every 3 years typically. With the EC, with the Veris machine, that's a one-time thing. We only have to run that once, and then we have those zones. So that answers that question.
Great. Thank you guys for those questions, and Todd for your time today. We appreciate everything you do for the 4R Alliance.
Thanks for having me.
No problem. Next up, we have Sally Fliss with the Fertilizer Institute, and she's here today to talk about the case studies that the 4 R's have completed.
Good morning, everyone. This is Sally Fliss, Senior Director of Agronomy at the Fertilizer Institute in Washington, D.C. And today I'm going to talk about our 4R cost case studies. First, just a little bit about who the Fertilizer Institute is. The Fertilizer Institute is the voice of the fertilizer industry, and we represent everything from manufacturing to on-the-ground retail sales. We are based in Washington, D.C., but we do work directly with farmers, work with agencies like the U.S. Department of Agriculture. And one of the big things we've gotten behind in the last almost 10 years now is research around the implementation of 4R nutrient stewardship practices. And we were successful in getting some language into the 2018 Farm Bill to help increase funding for research projects in the 4R area. 4R nutrient stewardship, hopefully everybody on the call has heard of 4R nutrient stewardship. It is thinking about the right source, rate, timing, and placement of nutrients as we apply them to the field. But it's really more than that. You need to consider our soil characteristics, our site-specific data like slope, distance to water, other conservation practices, figure out what our crop yield and quality goals are in order to make those 4R decisions. Take into account the weather and things like soil temperature as we decide our nutrient applications. And most importantly, what do these practice changes cost the farmer? So in the pictures on the screen, you'll see taking some soil temperature to see where we're at for nutrient applications, looking at the soil type that's in the photo with the 2 gentlemen. You see a pretty sandy soil type there, and figuring out how do we need to time and what source is best used in a soil type situation like that. And then in the in-season application in the field, you'll see some slope, you'll see some buffers along the bottom edge of that field. You can also pick out a little bit of the variability in the corn that's growing out there. So all these are things we need to take into account as we're making our 4R nutrient stewardship decisions. Cost, however, is one that we know farmers and CCAs and ag retailers are thinking about all the time. The number one response from a survey that the Fertilizer Institute conducted for what do they want to do when they're working with a farmer, or what do they want to know about a practice that they're going to implement on their farm, is how is it going to improve the farm operation profit. The barriers that farmers and ag retailers and CCAs see to adoption of these practices are things like, is it going to require the purchase of new equipment, labor, or other one-hour time changes it takes to do different management in the field? And will they need to consult or find some other expertise in order to be able to implement the practices? One thing that's a bright spot out of a lot of these surveys is that the top 2 sources of information on fertilizer and fertilizer management practices are the agronomist and the fertilizer dealer. And so as crop advisors and agronomists, we have a great way to reach farmers with what we can do around implementing more advanced practices. And what we've done at the Fertilizer Institute is go out and create some cost-based case studies around implementation of 4R practices. All the case studies that we have done so far, which there's 12 of them, can be found on 4rfarming.org. And in order to create the case studies, we worked with our 4R advocates, and this slide shows our 2024 advocates. The advocates are an ag retailer and a farmer pair that are selected each year in order to showcase the good work that farmers are doing in the field. 2021 will be our 10th year of 4R advocates, and applications are open now, so visit nutrientstewardship.org in order to find those applications. Just one of the other things we like to do with the 4R Advocate program is really showcase the diversity of how and where 4R works. And so we've got, we start in the top left-hand corner of the slide, the smaller image. That is a strip-till farmer using a soil warrior. They're in Minnesota. And next to that, the longer photo, that is a very large, I think they're around 20,000 acre farm in Florida. They grow sugar cane, sweet corn, and other vegetable crops. The picture in the middle is a Pennsylvania, Maryland farmer, and that's a small orchard grower there. We do have a couple of other advocates in the area. One of them, I'll talk about their case study today. And then we've got a Missouri corn grain farmer and a Texas cotton grower. The Texas cotton grower is kind of an interesting story. He grows both organic and conventional cotton. And so as we do these case studies and as we work with our advocates, we're really trying to show that 4R works for everybody and has a place in all management systems. So specifically for the case studies, the data that we collected was 4 years of data at a whole farm average level or for individual fields over 4 years. And what we collected was really just those costs associated with implementing nutrient management practices or applying a fertilizer or nutrient to the field. So for example, if there's a corn starter that goes on at planting, then the cost of the planter and the tractor are accounted for because there's a nutrient application occurring then. If there is no starter going on with the corn seed, then we don't count the cost of the tractor or the planter for that application because there's no nutrient application associated with that. We do account for that equipment costs, both time and fuel use, so both a variable and a fixed rate price for equipment. And our fertilizer price is based on those prices that are reported to USDA. We also include costs for things like soil sampling, so whether you're doing a grid or a zone, how those soil samples are taken, cost for software that the farm might be using, cost for any GPS or GIS service and guidance that they could be using in order to make some of those variable rate applications or to collect yield information. We then group the practices by basic, intermediate, and advanced. And this example is for corn in the West. There is a table like this for Eastern small grain production, or Eastern grain production. So you'll see here kind of how we progress, what the practices are that are added as we go from a basic 4R to an advanced or emerging 4R nitrogen management program. You'll see we're shifting to more in-season application, and as we get to the advanced row, we're trying to split up those applications as much as possible to match the crop's growing cycle, accounting for any in-field variability, and using tools or sensors in order to help us achieve some variable rate applications. With some of the research that we funded through the 4R Research Fund, we were able to tie nitrogen oxide emissions to nitrogen management systems or 4R management systems. And it's related to the net nitrogen balance. And what we found is that at that intermediate level of practice implementation, if we reduce our nitrogen balance by about 33%, and that equates to a 7% reduction in nitrous oxide emissions. When we compare a basic 4R practice to an advanced or emerging 4R practice, we can reduce that nitrogen balance by about 66%, which results in us being able to get a 14% credit for reduction in nitrous oxide emissions. Starting with some of the detailed case study data, this is a farm in Illinois. This is one of the first ones I worked on, and so it's one of the ones that I know the best, so that's where I always start with this one. So this farm went from some basic to some advanced practices in a pretty short time period. That's one of the other items we're capturing in the case studies is how does this change happen on each individual farm? You know, this farm went pretty quickly over a 3-year period into those advanced practices and continues to try and be more and more advanced. And then we've got some farms that are, takes them a little longer to test out these practices and decide what really works for them and maybe at an intermediate level for longer. On this farm though, in particular, as he switched to advanced, he went to all in-season applications and is doing an application as late as possibly V10. And what you'll see is that he decreased his cost per acre. He does manage some of his fields on a grid-based variable rate and some of them on a zone-based variable rate. So there's some difference in the consulting costs is really what the difference is on those two systems. But either way, he saved anywhere from $15 to $24 an acre as he moved to those advanced practices. Yield increased over those same 4 years, but I'm sure that's due to a larger combination of practices and not just his 4R nutrient stewardship. We're also able to look at some of those environmental metrics, as I mentioned. And so as he goes to advanced, he is increasing yield, decreasing his nitrogen application rate, which results in better nitrogen use efficiency. You can see he is getting down to 0.8 pounds of nitrogen applied per bushel of corn that he's harvesting. Now, one thing to consider on a number like that is, when do we get to a point where maybe that nitrogen use efficiency is too low? And as we think about soil health and some of the sandy soil conditions, especially in the Delaware-Maryland area, are we getting too low on those nitrogen use efficiency numbers and starting to pull nitrogen and carbon back out of the soil and going the wrong direction on some of the soil health? The same thing with the nitrogen balance, you can see is starting to get a little bit negative there. But one of the numbers that's really exciting to look at is this carbon dioxide equivalent emissions. That should be pounds per bushel of corn produced. And so what we see just from implementing his 4R practices and not taking into account things like changes in fuel use is that we can achieve about a almost a 35% reduction as we go from basic to advanced practices on this farm. So this number, I'll get to a slide a little later where we start to compare some of the corn numbers across farms and across states. But that's a pretty big decrease when we think about some of the demands that are being put on farmers from food companies for being the party responsible for helping to reduce their emissions. Just to touch a little bit more on that nitrogen use efficiency number, this is flipped equation. So the International Nitrogen Expert Panel put together this table to try and help figure out what is that range we want to be at before we're risking mining nitrogen out of the soil or we're in that inefficient nitrogen use area. And so here we're dividing our nitrogen harvested by nitrogen applied, again, which is the opposite of the number that we usually look at. Well, not the opposite, but here we look at total nitrogen harvested and not bushels of corn grain. Again, for this farm, we start to see as we get out to 2017, where he's getting pretty efficient, we are getting into that range where we're risking mining soil nitrogen from that system. So Lindsay asked me to touch on our Virginia corn grain case study, since you guys are operating in that area. And so this is a 4R advocate that we worked with to look at what he's doing in his farm and how does the case study look for him. So just a little bit about what the farm is. He's got some pretty sandy soils, as you guys are aware of. There's a lot of environmental concerns in this area. He does fall in the bay drainage area, and so he's got some very advanced practices that they've been working on for a long time because of the pressures around water quality in the Chesapeake Bay. He works really close with his CCA to adjust those fertilizer blends and incorporate things like micronutrients as a part of his nutrient management plan, all trying to work towards improving soil health on the farm and understanding the whole system. He does grid-based soil sampling and also uses in-season tissue sampling to help verify those numbers and adjust plans through the season. In addition, he's implementing other conservation practices on top of his 4R conservation. He does use cover crops in his system, no-till, buffer strips, and grass waterways. So that's a lot of other practices to take into account, and nutrient uptake by things like his cover crops that he takes into account as he is determining things like nitrogen application rates. He does apply all of his nutrients in the growing season and uses the protected fertilizer sources. So either a urease or a nitrification inhibitor or a combination product or a protected product like a polymer coated fertilizer when it's appropriate, depending on those weather conditions. As I mentioned earlier, he's doing grid-based soil sampling, so he is doing variable rate fertility prescriptions as he applies them to his field. So now to get into the results of his case study, What we found is that he has reduced his cost from 2014. He's been advanced, as I mentioned earlier, for quite a while, and that's because of the difference in those environmental pressures that we see on the East Coast versus when we work with some of our Midwest farms that are not in the same situation as you guys are in the Delmarva region. So he's really been a pretty advanced operator for quite a while now, going on almost 10 years in this farm that he's been doing really advanced management. But he continues to tweak that system and adjust with things like the tissue sampling and use more advanced technologies and add some advanced variable rate practices to it. And so you'll see from 2014 to 2016, he reduced his cost per acre by about $20 an acre by just continuing to refine those systems. Now in 2016, he had some weather impact on his yield, so his yields were a little bit lower. But you do see from 14 to 15 that he is gaining some yield. His nitrogen application rate is staying pretty average across the whole entire farm. And that's one of the challenges as we talk about what are the advantages to practices like variable rate is when we average this on a whole farm basis, our average application rate can often look the same, even though we're going to have areas of that field that are much more efficient and may get higher or lower application rates based on that yield history that the farm has established. But because of the yield increases that he saw, we see nitrogen use efficiency coming down on that farm. He's at 1 pound of nitrogen per bushel of corn grain, which is below that kind of average recommended 1.2 pounds of nitrogen that we need for corn grain. So we're making advances there. His phosphorus application rate stays pretty standard, and that's only going down as a starter that's placed below the surface, so really low risk of loss on any of that. His nitrogen balance is in a range that would be considered to be environmentally friendly. So we don't want to have a negative nitrogen balance, and we don't want to have too high of a nitrogen balance. The problem with a metric like nitrogen balance is you'll see when we look at a year like 2016, because he had weather impacted crops, we see that nitrogen balance creeping up. Now that's likely a case that a side dress application went out and then the weather impacted that crop, and so that nitrogen wasn't recovered in a growing crop. But it just means it's a metric that can be interesting to compare over seasons and can be interesting to compare across a farm and among fields, but we need to be sure we understand all the things that went into creating that nitrogen balance number. So what are all the things that impacted that 40-pound increase from 2015 to 2016? Wasn't a change in application rate, it was really just that impact of the weather and the yield on that farm. And so then we see the same thing in his CO2 emissions, that there's a higher risk or potential for those carbon equivalent emissions because that nitrogen wasn't captured in the corn plant. It was out there and could potentially be converted to nitrous oxide. As I mentioned earlier, we've got 6 case studies on the website that focus on corn grain. And so what that's let us do is take a look at how does this perform across the US and across different grain management systems. So we've got 3 no-till systems in there in 3 different states and 3 strip-till systems in there in 3 different states. So Ohio, Illinois, Virginia, Minnesota, and Iowa are the states that we've got farms that we have case studies on. And so you can also see that variation of the average corn grain bushel yield per acre that's reflected in that geography as well. But what we see is that as we move across all of these, we see a range in the CO2 reduction. And that's because, as I mentioned earlier, we see a range in the way and the rate at which farmers are adopting new practices. So not everybody's going to go out and be like that first Illinois farmer that's right on the cutting edge all the time. But even when we aren't going to the most advanced practices, we can still see as much as a 10% reduction in that emission. So we're covering about 13,000 acres in this data set. And this is going to continue to grow. We hope to have another about 20 case studies posted to the website in the next few months, and more of them will focus on this corn grain piece of it. So we're going to be able to continue to look at sort of what are the trends across the system. And all these farms reduce costs by anywhere from $10 to $25 an acre as they made these practice changes as well. As I mentioned in our 4R advocate slide, we do like to try and demonstrate that 4R is for everybody. So on our 4rfarming.org website, we've got case studies from strawberries, chips, potatoes, cotton, corn, grain in a bunch of different states. And coming soon, we're going to have some Wisconsin case studies where we look at corn silage and actually get some really neat insights into diverse crop rotations impacts on the cost of 4R, nutrient use efficiency, nitrogen management decisions. It's really nice to see in those case studies how, as we're coming out of an alfalfa rotation, farmers are adjusting nitrogen applications for that first year corn. So farmers are doing, as you guys know, farmers are doing the things that we say they're doing by accounting for all these nutrients as they make their 4R management decisions to really get the best use of what they're applying. There's also some good examples of how accounting for manure nutrients interacts with our fertilizer recommendations and applications in those systems. So those should be out hopefully by the end of the year, if not sooner. And so keep an eye out on our Twitter feeds to see some new information as it becomes available. Finally, here's some other resources we have. Again, nutrientstewardship.org for our advocate applications are open right now. So if you know a good pair of a 4R of a ag retailer and a farmer that would make good 4R advocates, again, this is our 10th year. So we'll be doing hopefully be doing some extra celebrations of the fact that we've got 100 advocates total. 4rfarming.org is where you can find all that detailed information on the case studies. Follow us on Twitter, and we've got some videos available. Thanks for the time today, and I appreciate being able to get to share our case study work. It's been really exciting to get to work with the farmers and learn more about what some of the systems I'm familiar with are doing and get to learn about some of these more diverse systems like strawberries.
All right, thank you, Sally. Sorry for that moment. All right, I currently do not see any questions in the chat box right now. So if you have any questions for Sally, you can enter them in there at this time. I would like to point out that the Fertilizer Institute is also a sponsor for today's event. So Sally, thank you for your time and for your sponsorship.
Yeah, it's glad to be able to participate. Wish we could all see each other.
All right, so Sally, we don't have any questions at this moment. If we have any, enter the chat box. Would you mind answering them so that everyone can check them out later?
Sure, no problem.
Thank you so much. We appreciate everything you guys do for us.
Hey, good morning, everyone, and thanks to the Delaware-Maryland 4R Alliance for inviting me to speak to you today. My name is Kelly Herbick, and I'm the North Atlantic Area Digital Services Manager, covering that region in the map that you see there on the right. I work with the local Pioneer team, representing the Corteva and Granular digital brands. The Pioneer team for this region is led by Kim Phillips, the district leader, and her team consists of several territory managers and field agronomists. So Joe Mayer covers the area that you see on the map in blue, Jonathan King in orange, Chris Skuse in purple, and Kelly Dietrich in green. And those territory managers are supported by a tech team made up of 2 field agronomists, Ryan Permilia and Patrick Watkins, as well as a product agronomist, Derek Bowman. And the reason that I'm showing you all the names and faces here as we get started is, as you're listening here today, if you have any questions or want any more information as we go through the presentation, you can feel free to contact me directly, or you can also reach out to any one of the individuals that you see on the screen here for more information. So as we jump right in, you'll probably notice that the title of my presentation was Using Variable Rate Nutrient Management to Your Advantage. And when we think of the 4R principles of right source, right rate, right time, and right place, our ultimate goal is to answer some agronomic questions that help us manage input decisions more effectively on our operations. But when we think about how we can start to use these 4R principles to our advantage, it's starting to understand how decisions that are agronomic can also be economic in nature and how they can impact our ROI and our bottom line. So as we can answer that final question on the slide there, how much does it cost? That gives us the opportunity to make better decisions in a given year, in a given field, but ultimately in the long term for an operation. So our granular software enables us to do just that. It enables us to consider return on investment as a driving factor in all of the agronomic decision making throughout the year. So we start with map-based planting plans that are developed in the winter months that hone in on hybrid-specific seeding recommendations. And then we can follow that up with variable rate nitrogen, fertility, and lime prescriptions generated to really protect that genetic investment made on a field-by-field basis. Then as we round out the end of the season, we can come back, do some post-season analysis once we get our harvest data in that helps us understand how those decisions actually impacted our bottom line. So the goal then is not only to help make seasonal decisions, but to then also understand how those decisions can and should change with time so that we can make better decisions year over year for the long haul. So when you look at the screen, obviously there's a lot that is included in a variable rate program, a lot of different decisions that can be affected. And for today's discussion, I wanted us to really just focus in specifically on fertility recommendations. And we'll talk about how moving to a variable rate fertility program can help manage fertilizer placement to reduce loss, as well as to improve the short-term and long-term ROI on an operation on a field-by-field basis. So if we jump right in, let's start by comparing some generic assumptions on these two programs. Now, when we think about a flat rate program, we're looking at pulling a composite soil sample within a region that represents typically a relatively large number of acres. So sometimes that's a whole field boundary, or a whole field boundary, which can be 25, 30, 40 acres. Or sometimes that's, maybe half of a field or a zone within the field, but it still tends to represent, 10, 15 acres and oftentimes. Once we pulled that sample then, we're making the assumption that that soil sample represents that region. And then we're managing our input decisions across that entire area based on those sample results. We're always working to stay compliant with our nutrient management plans through that process. And because we're not really always treating the field variability, we can find that we uncover the perception that the rates that we're able to apply conflict with the yield goals that we have on a field. So if we're trying to lift our yield potential year over year, but we're limited by the soil sample that was pulled, that can create a situation where we're not working together in terms of the recommendation and the farm goals to actually improve yield over time. Now that can be true or false depending on the detailed scenario, but what happens when we move to a variable rate type system where we're looking at smaller subfield units, we're looking at a 2.5 acre grid, for example, we start to manage those input decisions based on a smaller area within the field. And then we can adjust those rates to that region for the yield target that's associated with that area of the field. Now, always trying to maintain compliance with the nutrient management plan. What we find here, though, is that we can maintain compliance. We can follow the nutrient management plan guidelines while changing that perception. Because as we move to that variable rate program, we're working on a process to actually improve the yield potential in the field by lifting the lows and the highs together while maintaining compliance with a nutrient management plan. So what I see happen is, a shift in thinking and how we can, work through this process together. So let's talk about the zones then, right? If we're going to do this effectively, if we're going to do this well, we have to have really good subfield decision zones. And we start by looking at historical yield as a driver. And so if you look at the screen here on the left, you see 2015 corn harvest added to 2016 corn harvest, followed by the 2017 bean harvest. and we take those 3 years of yield data and we run that through a multi-year yield analysis to create a surfaced yield productivity index. And so on the far right, you see the field boundary with 3 colors in it. The green regions represent areas of high productivity, pink is average, and then blue are areas that are lower yielding or below average productivity. So this gives us a really good starting point to understand the potential of a field. The next step then is to really support that productivity index with additional data-driven layers. So this is where we can tap into our SSURGO soil database and all the soil classification characteristics behind it, combine that with our environmental response units, which allows us to bring in elevation data and refine those soil types. And then when we intersect that with a multi-year yield analysis, we can ultimately end at a granular agronomy management zone. So the map here you see on the far right now has smaller subfield units, more variability that you can see across that field, as well as a different color range. And now here what you're seeing in the color range is a productivity index, green good, green being your highest productivity, all the way down to red, which are areas of below average or low productivity. So this is where we can start to marry what we know about the soil with what we know about the production and the goals of the farm. Now, once we have those decision zones set up, it's really important that we have a conversation, what is the local decision that we want to make in terms of the yield potential for that field? And so there's multiple approaches that you can take here. And I'm just going to compare again to a flat target versus a yield target. So yield targets are set with the considerations of what are the past 3 to 5 years of yield history tell us about the yield potential for that field. And then we have to stop and consider, is that a good starting point? Is the yield target that we have a true reflection of the yield potential of the field? And so this helps us to understand what are maybe some agronomic considerations that we need to keep front and center before we make a recommendation. So a good starting point often in this scenario is to keep a flat yield target on the field across the boundary to reduce the variability that we're trying to test against maybe our soil types. This can help us get a sense for what the true limiting factors are in that field. Another option then on the right is to use a variable rate yield target. In this case, we have a good sense for what the limitations are, and we're able to distribute the yield across those management and productivity indexes that we created. So if you look at this example here on the screen, obviously red is the flat yield target. So we're treating that field as, has the same productivity across the entire field, even though we have zones lying beneath it. So if we would assign a 224 bushel target to both of these fields, the field on the right, we would actually distribute that yield potential across that boundary. So in this situation, in this example, we have some areas of the field that are going to go as low as 170, while other areas of the field have the productivity potential of yielding 270 bushels. And so this allows us to treat those regions uniquely different versus taking maybe the same approach on that other scenario, which is that flat yield target. So there's good agronomic decisions why you may choose one or the other, but this system gives us the flexibility and the option to pick the right decision for a given field. Now, once we have those yield targets set, then we've decided the right approach, we're able to handle the sampling workflows, determine the nutrient needs based on our granular agronomy equations, and then deliver specific variable rate fertilizer recommendations. And you can see that in the screenshots here. And we can create reports for each one of those steps. But as I mentioned earlier, with ROI being an important factor in the final decision that's made, this approach that we're talking about enables us to compare multiple strategies, associate a cost with those fertilizer sources, and then compare and contrast what's the best approach or the best method for a farm to choose to employ in a given year. So this allows us to really make a good, sound plan that's both agronomically good for the field, but also then economically feasible for the operation. Now, if you followed me up to this point, I think oftentimes a question that most people ask and should be asking is, this all sounds great, but what calculations are you using to make the recommendations? And Granular's got preset or standard calculators that are commonly used in the Corn Belt. These are the Tri-State, Illinois, and Iowa calculators. But we also recognize the regional differences that we've got as we move outside that Corn Belt geography. And we choose to work with local agronomists, reps, and CSAs, which are our certified services agents, to customize calculators that fit the specific needs of a region. So we call this a custom calculator or a custom equation. A really good example of that from the Northeast is a calculator that we built for the state of Maryland that allows us to write variable rate P, K, and Lyme recommendations that are compliant with the nutrient management plan guidelines. And that calculator was an effort between one of the field agronomists that you saw on the screen there earlier, Patrick Watkins, working with some of the local certified services agents to work with our agronomy pro services team and actually build those equations out and get them into the system so that we can make really good agronomically sound recommendations. So let's actually look at an example. And so this is a field from the state of Maryland that we walked through the exact process that I talked about earlier. So first step is we created that multi-year yield analysis. We intersected it with our soil types and our environmental response units, and we produced this productivity zone based decision map where we've got all of these subfield zones identified within that field. Now, the first recommendation and probably the number one value that we see with a grid sampled and variable rate program is the Lyme recommendation. And so if you look at the map on the left, you'll see this field has a 2.5 acre grid pattern pulled on it. And we see soil test values coming back all the way from a 6.0 to a 6.7 in range for pH. Now, the average of this whole field, assuming you got really good representation of the entire field, would have come in at a 6.4. And so if you look at the guidelines, a 6.4 is going to call for no Lyme applied. But when we move to this grid sampled pattern and we write a recommendation for this actual field, what we end up seeing is that we need 635 pounds per acre on average, but we need about 1,700 to 2,000 pounds in certain areas of that field to actually improve the soil potential and the yield potential. So obviously this is a number one starting point. If you can get this right and you can get your pHs ironed out across the field, that's going to be the foundation then to improve nutrient availability for all of the other inputs. And so this is, in my mind, absolutely the number one value in grid sampling is getting to that variable rate Lyme application. So if we continue on with this field and we look at making a phosphorus recommendation, what you're seeing here are the soil test values now, the P values, that we are intersecting with the management zones. So on the left would be your traditional grid sampled method of just pulling the soil data. And on the right side, what we did is we chose to actually intersect those soil test values with the decision zones that we created. And so these are two different methods for how you could write a variable rate fertilizer application for this field. So let's take a look at that. So we did just that. We assigned a 230 bushel yield target. And if you think back to the discussion that we had here earlier on the methods for assigning a yield target, in this situation, we went with a 230 bushel flat yield target for the entire field because we wanted to understand if we can correct our soils, does that change the productivity indexes in the future? And so when you look at the recommendations here, on the far left, we've got a 2.5 acre grid MAP fertilizer recommendation calling for about 255 pounds. The zone-based MAP fertilizer recommendation is calling for about 249 pounds per acre. And then if we compare that to what your average flat rate recommendation would have been, it would have been 257 pounds per acre. So you might look at this and say, oh, well, there's not a big difference in these three programs and the total fertilizer demand. But hopefully you can quickly see that there's a pretty significant difference in the actual application of where that fertilizer is recommended to be applied to the field. And again, in this situation, we're just treating the soil variability. We're just treating the soil variability versus that flat 230 bushel yield target. I'll walk through this example pretty quickly, but kind of same concept, two different methods. Grid sample on the left intersected with the decision zones on the right. And when we turn that into a potash recommendation, against that same 230 bushel yield target, again, we run into a scenario where we've got very similar average rates, 139 in the grid program, 126 in the zone program, and 132 in that field composite or flat rate recommendation. So again, very similar programs in terms of total units needed, but very different placement in what we're actually seeing a recommendation come out as. Now you may notice a pretty distinct difference between, the map on the left with the grid pattern versus the map in the center with the decision zone based program. And the reason for that is because we're interpreting those soil test values a little differently. We're basically moving them into that grid or that zone pattern. And so it allows us to look at those values a little differently than actually just treating them as 2.5 acre grids independently. So there's merit in both approaches. It really just depends on, what makes the most sense for the producer and the agronomic knowledge of that piece of ground. Now, if you think back to the previous pictures that I showed you in the last few slides, I intentionally cut the field out of the map. I didn't want you to see the map around the field. And I did this for a reason, right? So this is the same field, and this is harvest data from one of those 3 years. And what you're seeing here is obviously green is good, higher yield potential, red is bad, lower yield potential. But you can see around the field edge here that, if you farm in Pennsylvania, Maryland, Delaware, we've got a lot of fields that border woodland. And in these situations, we have a lot of wildlife feeding and wildlife damage. And so what we're seeing here is some of these zones in the field are driven not necessarily by soil productivity, but by yield potential being limited by wildlife. And so if we look at the recommendation that we would have made here, we're trying to build our soils because we had some low test points come back here, but we're also trying to build to 230 bushel yield in an area that likely will not see 230 bushel yield. So in this situation, what we're going to end up doing is, because we're limited by animal feeding, we're going to over apply whatever, MAP or potash to these sections of the field because we're trying to meet that crop yield removal or crop goal, right? The crop removal credit that we're trying to consider while we also rectify the soils. So if we start to think about this scenario and we look at a yield target approach like we had compared and contrasted earlier, what the yield target approach is actually going to allow us to do is consider the agronomic implications of what's happening locally. So we're probably not going to change the animal feeding on the margins of this field. So we don't necessarily want to apply fertilizer for 230 bushel corn in these regions of this field. So instead, we can call back the yield target here. We can increase the yield target where we have the potential of hitting that higher yield ceiling. And we can make the recommendation that not only helps us to improve the soil test values, but also is applying the right rate for a realistic yield target within that region. And so this is where I think what gets me excited about it is we can have a conversation locally. We can understand what the right approach is for an actual farm and field and make those decisions. And so the system, with the flexibility that we have here, allows us to compare all of these different strategies and pick and choose the one that is right for the farm. So it's not that one's right and one's wrong. It's a matter of determining what the best approach is given the knowledge that we have on that field locally. So as I wrap up here, I mentioned earlier that the ultimate goal is really to combine the economics with the agronomics. And hopefully as we went through this, you can see how variable rate allows you to really micromanage your inputs and unlock more opportunity there. But with our granular agronomy program, we also have a granular insights product. And that granular insights product allows us to actually track all the inputs that we've got on a field by field basis. And sorry, not all the inputs, but many of them. So if you look at the screenshot here, we can add and adjust our seed cost, our nitrogen cost, phosphorus, potassium, herbicide, fungicide, other costs that you would want to apply to a field, and even include your land cost in there. And the value in this is if you go in and you plug in your values it'll start to pre-populate with just some default values off of some industry averages and university research. But once you populate your own farm data, you can start to get a sense for what inputs are driving revenue across the farm, what fields are more productive than others, and really start to troubleshoot why. What you see on the right then is a profit map. And that profit map is looking at your seeding layer and the cost associated with the seeding layer compared against the harvest layer. So if we know how many seeds we planted in that field and we know how many bushels we removed from that field, we can then produce that map that gives you an indication of what areas of the field are you making money on versus areas that are maybe costing money to farm. So these things working together can really start to help us understand, how these inputs are being utilized by the crop in the field and help us to make decisions that allow us to maximize, where we're spending our dollars. So I would really encourage you to explore. There's a free version of that Insights product out there. You can just go to the App Store and download it and start to play around with how that product works. And then if you have questions on granular agronomy or getting into some of those variable rate techniques that we talked about, again, you can feel free to contact me or any of the folks that I showed you there on the screen earlier. So with that, again, thank you for letting me speak to you all today. I appreciate you paying attention and listening to the presentation. And if you have any questions, you can feel free to email me, Kelly Herbick, KELLYHERBICK @granular.ag. Thanks everyone and have a great day.
Thank you, Kelly, for presenting with us today. It is excited to hear all about variable rate. If you have questions for Kelly, you can enter them in the chat box at this time. Kelly, we do currently have one, so if you're ready, it is from Sally. She asked, are you able to map any environmentally sensitive areas along with the P variable rate recommendations?
Sally, I guess, and maybe I don't fully understand the question. In terms of mapping capabilities, we can map field boundary, any boundary that we want to put in the system and pull in the soil data and layers behind that. In regards to environmentally sensitive areas, I guess I'd ask for a little bit more information to help me answer the question.
So Sally added low areas close to streams.
Yeah, again, so you could map any areas of a field. We cut out boundaries or we can create buffers around areas where we don't want to apply or make a recommendation. So we could manage that through the mapping side of things.
Thank you. We have another question that says, if you have 5 years of yield data, do you include or throw out highest and lowest yield years?
So I think that question was from Carl. So Carl, we typically manage that in combination working with a producer to understand what yield targets they want to, what yields they want to include. Oftentimes what we can find is that if we look at 10 years of yield history when we're making the zones, there could be some years that we want to suppress because of agronomic considerations or agronomic concerns within a region. So if we had extremely dry or extremely wet years, we may decide to suppress those years of data when we make the zones. The zone creation process, though, is distinctly different from the yield target that is set on the field. And so when it comes to actually setting a yield target on a field for a given year, that's when we would follow the local guidance, working with that producer to adjust the yield target based off of their 5-year average. So yes, that's the place where we would remove the highest or lowest years when we set the yield target on the field for the upcoming growing season. But they're two distinctly different discussions. One is around creating the zones or the productivity within the field. The other is around what is the right yield target for a field in a given year.
Thank you, Kelly, and thank you, Carl and Sally, for your questions. We really appreciate it. If you have any other questions for Kelly, you can add it to the chat box and she can answer them through that. Thank you so much, Kelly. We appreciate your time. we will continue with our last speaker at this time. If you have questions for any of the past speakers, you can still enter in the chat box and mention who it is directed to, and we will work to answer all of them. Thank you guys so much and enjoy.
Our next presenter is Mark Williams, joining us all the way from West Lafayette, Indiana. Mark is an agricultural engineer at the USDA National Soil Erosion Lab in West Lafayette, Indiana. He studies subsurface hydrology and nutrient transport at the field to watershed scale. He also tests and evaluates the effects of conservation practices on water quality. While he spends most of his time working on subsurface drainage and phosphorus loss in the Lake Erie region, he also collaborates with colleagues across North America as a part of the USDA Long-Term Agroecosystem Research Network and the Conservation Effects Assessment Project.
Hello, everyone. My name is Mark Williams. I'm a research engineer with the USDA National Soil Erosion Research Lab in West Lafayette, Indiana. In today's presentation, I'm going to be talking about the 4 R's and specifically about phosphorus placement. So the first thing I want to start discussing today are the different types of phosphorus. So the first type of phosphorus is fertilizer P, and this is phosphorus that's been recently applied. And it is this phosphorus that is at an acute risk for phosphorus loss during a storm event, let's say immediately after application. The second type of phosphorus is legacy phosphorus, and this is often referred to as soil phosphorus as well. And this type of phosphorus is at a chronic risk of phosphorus loss over time. So this is phosphorus already stored in the soil that can be lost over long periods. And it's important to remember that as we talk about the 4R practices, the 4 R's address the acute risk of phosphorus immediately after application. So we're talking about fertilizer P in this presentation. So from a dissolved phosphorus perspective, you can't go wrong with subsurface placement. And since this is a virtual presentation, and you can turn me off whenever you want to, I thought I'd start with the end message here at the beginning. And that's because subsurface placement will consistently reduce the risk of acute dissolved phosphorus loss, regardless of the other factors. And that means rate, source, and time. And why is that? Because phosphorus binds to the soil. So over the next 15 minutes or so, my goal is going to be to demonstrate the water quality benefits and the trade-offs of phosphorus placement. And I'm going to be largely looking at 3 different types of placement. Those are broadcast, incorporation with tillage, or injection and or banding. And to do that, I'm going to look at some lab, plot, and field data from Texas, Ohio, and Pennsylvania to show these results and explain the differences between the 3 placement methods. So the first, we're going to start off in Texas. And this first case study is a laboratory rainfall simulation. And it was comparing broadcast and banded phosphorus using 2 different phosphorus sources. And for each of these case studies, since it is a virtual presentation, again, I included the full reference down here at the bottom of the screen. So in case you're interested in looking at more information, you can pause it and Google this paper. So in this study, they used runoff boxes shown here on the left, which are essentially metal boxes packed with soil. And they were using a sandy loam soil from Texas, and they applied 20 pounds of phosphorus to these boxes, 20 pounds, equivalent of 20 pounds per acre. And they had 3 phosphorus sources. They used MAP, poultry litter, and they compared it to an unfertilized control. Then immediately after they applied their phosphorus, they did a fairly significant rainfall event, 2.5 inches per hour on these boxes. So jumping right into the results of this first case study. The phosphorus sources are down here on the x-axis along the bottom. So we have the unfertilized control, poultry litter, and the MAP. And on the y-axis, we have dissolved phosphorus losses in milligrams. So you can immediately see the difference between the two different treatments, the broadcast in the blue and the banded fertilizer in the yellow, where the banded fertilizer had much lower dissolved phosphorus loss than the broadcast. If we just specifically look at the MAP to showcase the difference between these two treatments, for the MAP, during that one rainfall event, right after they applied the phosphorus, the broadcast fertilizer, 17% of it was lost, compared to less than 0.2% of the loss or phosphorus when it was banded. So a lot of times, it feels like laboratory studies don't necessarily represent the real world. So let's look at some field results. And this is another study from Texas, and it was looking at long-term, that means over 15 years, examining poultry litter application to fields and pastures. So in this study, there was 6 fields and 3 pastures that were studied over the 15 years. It was a clay soil in a research site right near Riesel, Texas. The phosphorus rate ranged pretty considerably from 16 to 195 pounds per acre of poultry litter applied. For the fields, they were in a corn, wheat, fallow rotation with annual conservation tillage. For the pastures, they were usually in hay Bermuda grass, and they were not ever tilled. So if we compare the two different, the fields to the pastures over this 15-year period, let's look at some of the differences that this study found. First of all, the pastures had lower poultry litter application rates than the fields. That was just the design of the experiment. But as a result, the pastures had lower Malic-3 soil test phosphorus concentration. And that phosphorus was stored in less labile pools in the pastures, meaning that the pastures were generally, based on soil tests, less likely to lose phosphorus in runoff. But what we found was that the pastures actually had a greater risk of dissolved phosphorus loss during this study. And that's because the poultry litter was incorporated on the fields, but broadcast on the pastures. And this is just one way we looked at this data set, looking at the average annual Malic-3 soil test phosphorus on the x-axis and the flow-weighted mean dissolved phosphorus concentration on the x-axis. You can see the two different colors here are the 3 pastures and the 6 fields, and how these pastures stand out distinctly from the cultivated fields, where even though they had similar soil test levels, the dissolved phosphorus concentrations were much higher in runoff from the pastures. So moving north to Ohio, this is a field study, another field study, examining effective tillage on phosphorus loss to tile drains this time. So the first 2 studies we looked at in Texas were on surface runoff, but now we're looking at phosphorus leaching to tile drains. So this was just 2 fields right across the road from each other. They were silt loam soils. The farmer applied 42 pounds of phosphorus per acre of MAP. These fields were in a corn, soybean, wheat rotation, and both of these fields had been managed as long-term no-till for over 30 years prior to our experiment. And our experimental treatments for this were that the one field, after the MAP was applied, it was incorporated with tillage, and the other field, the MAP would just remain broadcast on the surface. So to highlight the difference of the phosphorus placement, we're just going to look at the first rainfall event on these fields after the fertilizer was applied, where this graph on the left over here was the field that was tilled, And this graph on the right is the field where the phosphorus remained broadcast, or it was no-till still, or remained as no-till. And the red dots represent the dissolved phosphorus concentration. So you can see that in the no-till field where the phosphorus was broadcast, the concentrations of dissolved phosphorus were nearly 5 times greater than that from the tilled field here on the left. And these differences between broadcast and incorporated with tillage remained for several events after the phosphorus was applied. So here showing 7 storm events. 2 of the events occurred before the phosphorus was applied, and then we had 5 events after the phosphorus was applied. And you can see over these 7 events, the dissolved phosphorus loss in the tile drainage was only a quarter of what it was when it was broadcast on the surface. So let's look at another case study in Ohio, looking at 3 phosphorus placement treatments. So this is one of the first studies that we've talked about that now looks at both broadcast and tillage, but also banding and injection right alongside of it. So this study was done using rainfall simulation on some small plots. When we created plots on 4 different fields across northwestern Ohio that had varying soil types. And we applied 67 pounds of P per acre of MAP again. And again, our treatments were we had broadcast, incorporated with tillage, and also injected P fertilizer. And the results are more of the same, what we've already seen, where the broadcast fertilizer had much higher concentrations compared to either the inject or tillage. And we also measured particulate phosphorus, again, in this study, and this was, again, going to leaching to tile drains. And even though we tilled the field with the tillage treatment, the particulate P losses in the subsurface were less than that of the broadcast P in this study. So the broadcast fertilizer application resulted in greater phosphorus leaching compared to both injection and tillage. Now moving on to our last case study. This was both a combination of lab and plot study evaluating phosphorus placements in both runoff and leaching. So the leaching study was done in the lab, the runoff study was done in the field. So they used 2 different soil types, a sandy loam and a clay loam soil. They applied 30 pounds per acre of liquid dairy manure to both the lab study and the plot study. And the treatments were broadcast and incorporated. So for the leaching losses shown here, the top graph is the broadcast manure and the bottom graph is the incorporated manure. And you can see that the peaks are much greater in concentration for dissolved phosphorus loss for the broadcast manure compared to the incorporated manure, much like all the other studies we've already shown. But what I'd like to highlight about this study was they also measured what they did in the runoff. So here we see phosphorus losses on the y-axis. They show dissolved losses in blue and total phosphorus in orange. So here's before manure application. This is the broadcast and then incorporated. What was interesting about this study is that for the broadcast treatment, most of the total phosphorus was dissolved phosphorus. So that you can tell that by the similarity in the size of these bars. But for the incorporated with tillage treatment, most of the total phosphorus was in the particulate form, highlighted by the difference in the size of these bars. So the total phosphorus we lost between the broadcast and incorporated wasn't too terribly different, but the form of the phosphorus lost was. So let's think about coming back to this idea of trade-offs, and that kind of is highlighted in that last case study I just talked about. So if we just look at relative risk, so I classify relative risk as low, medium, and high. And we have our 3 different types of phosphorus placement here on the x-axis. And this is, the blue again is dissolved phosphorus. So in general, when you broadcast fertilizer and you leave it on the surface, this represents a higher risk of loss, whether it's in runoff or in leaching, compared to either banding or incorporating fertilizer. And these little lines I have sticking off here are the range in uncertainty. So just because you broadcast fertilizer doesn't mean it's going to be a high risk every time. You know, you could apply your fertilizer and it not rain for a week or two, and when it does, it's a small rain, so it doesn't generate any flow. So therefore, it probably wouldn't be a high risk. But overall, just looking at the studies that we've looked at, broadcast fertilizer application represents a higher risk of dissolved P loss than the other two treatments. But on the other hand, when you look at particulate phosphorus or phosphorus that's generally associated with erosion, you see just the opposite trend, where broadcast application has the lowest soil disturbance compared to incorporation, which would have the most soil disturbance. So in general, you're going to have a higher risk of particulate phosphorus loss when you incorporate compared to when you just broadcast it. And it's these trade-offs that make it difficult to decide what is the right placement. So I came up with a few questions that we should ask when we're deciding what is the right placement. The first question being, first of all, does the field need phosphorus based on soil testing? That's the most important question. If it doesn't need phosphorus, let's not apply it. Second question is this field prone to surface runoff or erosion? Because if it is prone to surface runoff and erosion, then anything where you're disturbing the soil is going to make it a higher risk for particulate phosphorus loss. And lastly, do the characteristics of the soil or the field drainage make it susceptible to phosphorus leaching? Because if it's susceptible to phosphorus leaching, then your main concern may be dissolved phosphorus transport. So if we look at all these questions, and if we want to decide what is the right placement, I came up with this general goal in deciding what to do. So the goal is to maximize soil fertilizer contact, but minimize soil disturbance. And that's going to be different for each individual fields, what that best combination is. But the goal should be to maximize the soil fertilizer contact, because phosphorus binds with soil, and that'll reduce our dissolved P loss. But at the same time, trying to minimize our soil disturbance to reduce the risk of particulate phosphorus loss. Another thing to consider when choosing the right placement is potential differences in crop yield as a result. So, as many of you know, phosphorus accumulates at the soil surface when it is broadcast, and this is called stratification. And that's largely because phosphorus, again, binds to soil and doesn't move really readily through the soil profile. But crop roots grow down into the profile. Therefore, when you apply phosphorus in the subsurface, the plant roots can have better access to this phosphorus. And I got this data from Doug Smith from USDA, and where he shows the relationship between soil test phosphorus and Malic-3 versus corn yield. So you can see on this top graph, the relationship between soil test level and corn yield isn't very good. There's almost no relationship for 0 to 2 inches. But when you move down to the 2 to 8 inch depth, the relationship greatly improves, where there's a strong correlation between Malic-3 phosphorus and corn yield. So putting the phosphorus in the subsurface can provide the plant with the phosphorus where it needs it, not just sitting on the surface. And again, here's another example of a similar type thing, looking at crop yield, but this time from the University of Maryland Eastern Shore, where they did some poultry litter application trials. And this data is from 2008 and 2009, where they have 3 different treatments, either no manure or surface or subsurface applied manure versus corn yield. And you can see that manure increased corn yield regardless of how the manure was applied, but corn yield was, in both years, was greater when it was applied in the subsurface compared to when it was just broadcast on the soil surface. So to summarize the things we talked about today, we want to maximize soil fertilizer contact to reduce the risk of dissolved phosphorus loss. But at the same time, we want to minimize soil disturbance to reduce the risk of particulate phosphorus loss. And the right placement balances these trade-offs between dissolved and particulate P based on differences in site and the weather factors. I would like to thank Lindsay from the Delaware-Maryland Agribusiness Association for inviting me to give this presentation. If you have any questions, you can ask me either during the live session, or you can feel free to send me an email. That's the easiest way to get a hold of me. It's mark.williams2@usda.gov. And thank you for watching.
Thank you, Mark, for joining us today and for your presentation. We appreciate everything that you have done. If you guys have questions for Mark, throw them in the chat box while he is on live with us. I would like to take a few seconds just to let you guys know, if you are joining us today through your phone or tablet, you can enter your CEU information through the Google form attached in the chat box. If you are on the phone, we will be emailing each of you the link to that as well. Please try to have all of your entries in by 4 p.m. this afternoon, and you do not have to enter more than once. If you enter once, you are good to go. So thank you for doing that and for your understanding. All right, Mark. We are not having any questions in the chat box at this time.
Yeah, if anyone does have questions, just feel free to email me.
Absolutely. Thank you for providing that information for everyone. So thank you guys for attending, and please enjoy the rest of our show.
We would like to thank you all for your participation in today's event and hope that you found the presentations to be interesting and informative. At this time, we would like to remind you to look in the chat box for the link to fill out the continuing education credit information for each of the respective states, as well as the Certified Crop Advisor program. If you have any questions regarding this event, please visit our website at 4rmidatlantic.com, where our contact information can be found. We would again like to thank our sponsors for their support of today's event and hope you all have a great rest of your week. Thank you.